We're going to do, let's take a look at the calendar. The calendar, we're sitting on the 12th today. All right. Probably going to do chapter 9 this week. Count on a test in chapter 9 near the end of in the next week sometime next week. I don't know how far we're going to get through chapter 9, but sometime early middle of next week, we're going to shift to chapter 10. And we're going to do chapter 10 through the end. It's the 28th, 29th, 30th, which is Wednesday, Thursday, and Friday. All right, Wednesday, Thursday, and Friday. Our final exam is Wednesday, 9/11 in this room. That's the first day of finals. All right. So what I've said the whole semester applies to these 2 weeks squared. You need to be as intense and as intentional as you possibly can be. Throw junk out of your schedule by the boatload. Very difficult to get time with you right now. Very difficult. And that means hanging out with friends or whatever. Because we've got ground to cover, and I know this comes at a bad time because it comes at a bad time for the for baseball season and just into the school year kinds of stuff, right? So really make a special schedule for this time of the year. Tonight is Spark, and I have till tonight to have made corrections to your exam. Okay, so if you want to do that at Spark, let me know. I'll take your tests there. If not, make plans this afternoon to come by and make corrections on that. All right. Let's get the recording going. Yeah, let's go. Here. Yeah, we have got ground to cover. I don't know if you noticed, but the just the chapter 9 slides is like 111 slides or something like that. It's crazy. All right, we're not going to make it through all that, but we've got all chapter 10. And it's important that we cover a lot of that in chapter 10. A lot of chapter 10 is not as difficult in many ways as the last couple chapters. So chapter 8 is kind of the most intense ones. You learn so many different techniques. And there's no faking it. And there's no faking this stuff either, actually. But, okay. So, but I'm here to help. Come. If you want to come downstairs, just hang out, work problems outside on one of those tables. Come in and see me when you need help. Something like that. That's a good plan. Some people benefit from doing that. But time on task is going to be the king there. Okay, so we'll back it up here. We were doing the integral test, and basically we saw that if something diverges as an integral from 1 to infinity, then it diverges as a series. And this was the P series. All right, P series. We're going to be doing that on the slide that we're starting from today. So keep that in mind. It converges if P is strictly greater than 1, diverges otherwise. So we go down here. This is, now, do you care that this starts at 4? No, you do not care that it starts at 4. You don't care. Now, it can't be 0, obviously. But if it starts at 4 or 1, understand that it will diverge if the tail diverges, because the first finitely many terms will not play into whether the series converges or diverges. Said differently, you can always ignore finitely many terms. You can always ignore finitely many terms. All right? So in this particular series here, one way we can think of this is here n N is, I'm sorry, P is 7. So this is a P series. Series P equals 7 is greater than 1. So what? It diverges. I'm sorry, converges. It's that simple. Now, the theorem technically says n equals 1, but it works for n equals 27, n equals 1,000,000. Because you can always ignore the first number of terms. That's just some number. So if it converges, it's going to converge with that number added to it. If it diverges and goes to infinity, it's going to diverge with that number added to it. All right, and oh, here it's over here. Duh. Okay, here, look. What is in here? In right? No. It. Oh, no. Check that. My bad. What is P?
1/2.
P is 1/2. Less than 1. Right? Therefore, diverges. Right?
That was easy.
Next one. P. Okay. Notice up here, P is -2. Okay. So in our example. But here, it has this theorem only applying if P is greater than 0. But remember that this equals, not equal. N to the -2 in the bottom is the same as n squared in the top. That certainly diverges, right? Because this equals 1 squared plus 2 squared plus 3 squared plus 4 squared plus ... That certainly diverges.
Diverges or
Diverges. That keeps getting bigger and bigger and bigger. That never stops. Okay. So that's why you can cross off this little part here, this little thing I have crossed off on the side. It diverges for any P less than or equal to 1. Any P less than or equal to 1. Even if P is negative. Because if it's negative, it diverges even quicker, you might say. All right. Now we're about to go into a bunch of series tests. Series tests. Now, where can I direct your attention to? Near the end of the chapter. Where's that here? No, that's not that. I'll find it. I have it in the slides. I have it in this. Oh, I try to put some of these historical figures in. You really ought to read those in the book. Some of them are very interesting. And I just happen to be looking here at one of my all-time favorite historical figures in mathematics, Srinivasa Ramanujan. He lived in the turn of the last century, 1880s to around 1920. Died very young. He was an Indian man, Asian Indian, and he's completely unique in all of mathematics. There's nobody like Ramanujan. And by the way, what the Indians and the Asians are doing today, they got the work ethic that Americans used to have, right? Because a lot of them are trying to escape such abject poverty. A lot, not all. There are well-to-do Indians as well, but a lot of them are trying to escape such abject poverty. They are studying calculus in tin huts at 6 o'clock in the morning. I'm serious. Going to work all day, coming back to school at 9 or 10 o'clock at night, or doing their studies at night, just to escape out of their situation. Americans, by and large, have it way too comfortable to be that motivated. But he, back in the 1880s, I want to tell you, India was a very poor country, very poor region. And he just was never challenged by any math in school. And he learned a lot of math on his own. He played around with math by himself. He'd get a hold of any math book he could, and he would master it in a very short period of time. The math he came up with he came up with it on his own. So he didn't follow any current lines of development in mathematics. So he didn't know what the researchers were doing at the big universities in Europe, right, or in the United States. He was eventually discovered by a guy named G.H. Hardy, who was a great mathematician. He was British. I think he was at Oxford. Is he in here? I think he was at Oxford. And G.H. Hardy is a master mathematician, one of the greats. And he left India and went to work with G.H. Hardy at in England. And his math was so advanced, nobody had done anything like this stuff, right? And it's not like it was even above other math. It was just different than other math. And he come up with formulas and different developments, ways of describing things that were so random looking, right, that people just couldn't believe it. Okay. Well, he went over to England. Unfortunately, there he didn't adapt well to Western food, and he was sick a lot in a new country, new environment. And his health began to fail. And so he stayed there, I don't know, just a few years, went back to India and wound up dying of tuberculosis at 32. But on page 673, there's a little spot dedicated to him. Okay, I'm not finding the page I'm looking for. Anyway, you're gonna have a bunch of tests, convergence tests, for series. And I told you before, they're all gonna blend together. They're all gonna blend together. You're gonna go, which one am I doing? Is this and that? I don't know. Can I do that one? I can do both. I hope my mommy. They'll drive you nuts sometimes. There's no substitute. You know what I'm talking about? Graphite to paper. Graphite to paper is the only method. So. First one is one that kind of makes sense. This is a more intuitive one, but yet it screws people up. Remember the if P then Q thing I did the other day in here? This is another one. This is another one. If a series converges, now look here. We have zero, you have series that are positive terms, strictly positive. And one series is bigger than the other series term for term. So B is the larger series. So one way of showing that a series, a positive series, converges is to show that a larger series converges. So look here. If this larger series, Bn, converges, then the smaller series converges. Because keep in mind that Bn is larger, or at least as big as An, for every value of n. So one way of showing something converges is to show that a larger series converges. Part one, that's part one. Part two. If the smaller series diverges, if An is less than Bn for all n, and the sum of the An's grows infinite, well, then the sum of the Bn's has to grow infinite because it's larger than the An's. If the An's is blowing up to infinity, the BNs have to blow up to infinity. All right. So don't let me catch up in my notes here. Okay. Question. So we can show that a larger series converges. Now we're talking all positive terms. We can show that a larger series converges or that a smaller series diverges. It doesn't do anything to show that a larger series diverges. Because if one series is bigger than another and that one takes off to infinity, it doesn't say anything about this one. But if this one is smaller than this one and this one goes to infinity, this one has to be infinite as well. Look at this guy. Question. Question. We're going to start comparing, right? And we have here, this is called the direct comparison test. Oh, by the way, DCT. Because we're lazy, right? Shake your head. Yes, we are lazy. So we're going to call DCT. We're not going to write direct comparison test even once because we are bottom-dwelling scum suckers. Question. This guy. All right. All right. What if we have to compare this to something. We don't have any way of looking at this and saying whether that converges or diverges by looking at the terms itself. We want to compare it to a series that is lower or smaller. And by the way, it suffices to say it's smaller from some point on. So this has to be true for all n or for n greater than or equal to some big N, which is a integer, positive integer. Use new notation here. Okay. That's another way of saying from some point on. All right. From some point on. So if it's true from some point on, we can ignore the first few terms. So down here, we ask ourselves, what are we going to compare this to? What are we going to compare this to? Right? Let me see. If we call this, if we call that some, that's our AN. We have two choices. You're going to have to start developing a sixth sense. Do we sense that that converges, or do we sense that that diverges? Right? Now, what other series does this resemble? We have, in fact, it resembles two other series that we already know. This resembles number one, sigma n equals 0 to infinity. 1 over 3 to the n. And it resembles sigma n equals 1 to infinity, 1 over n. It's those two added together in the bottom. Question. These two series, do they converge or diverge? We should know. If you spent time with us over the weekend, and wait till Cassie gets back too. If you spent time with us over the weekend, you would know what these two do, because we talked quite a bit about them. Tell you what I'm gonna do. We're gonna have pop quiz. I want you to write on your paper. Don't tell me your answers. Write on your paper whether these converge or diverge and why. Do a little Jeopardy jingle here. Yeah. Boom, boom. This guy here, that equals 1/3 to the n. And this converges. Geometric series with r less than 1. This is r right here. You missed a pop quiz.
Oh.
You have to make it up. You're gonna have to make it up. Just schedule it in the edge. These two series over here, they resemble this guy here. And we want to figure out if this guy diverges or converges. And the pop quiz was, what do each of these do? All right, the top one converges. The bottom one diverges. Why does it diverge? Well, we studied that one. That's the harmonic series. Right? Harmonic series. This is a P series as a P series with P equal to 1. Right? That's the harmonic series. 1 plus a half plus a third plus a fourth plus a fifth and so on. That diverges. P series of P equal, and that's the easy way of giving a reason why. Anytime you say a series converges or diverges, you need to say why. And in this problem, you need to compare it. The whole idea with the direct comparison test is you compare an unknown series with another series that you know that converges or diverges. You compare it with a series that you know. All right. Now, let's just, for example, let's treat this as sort of almost a let's treat this as a geometric series for the time being. Note. If this is AN, how does that compare to this series here? Call that one BN. How do those compare? Greater than or less than? They're obviously not equal. Should I put a greater than sign in there or a less than sign in there?
Less.
Less. It's got a bigger denominator, so it's less. Okay? So now, think about this a second. So sigma 1/3 to the n is a bigger series. right? We're applying our direct comparison test. So this right here consists of bigger terms than this. Okay? If a bigger series, all positive terms, it's got to be all positive terms. If a bigger series converges, the smaller one does. All right? So sigma 1 over 3 to the n plus n converges. So this is what your answer is going to look like. It converges by the direct comparison test since sigma 1/3 to the n equals 0 to infinity, converges as, why does that converge? As a geometric series with r, the absolute value of r, equals 1/3 less than 1. This is our r right here. Right? Okay. So we showed brackets. We showed larger series converge. That's using the direct comparison test. Right? It's very important that you state why. There's not a lot of work to be done. There's not a lot of computations here. This is like a good doctor, right? A good doctor looks at the situation, listens to your symptoms, and then doesn't check everything, right? You know what? We need to look at this in your blood, and we need to look at your bone density or something, okay? Right? A good doctor, for most conditions, some conditions are very complex. For most conditions, they know the things that will sort out your condition from other conditions, and which one of many conditions will apply. This is going to be the nuance in this whole chapter. Now, let's back up a second. We noted at the beginning that this series resembled this one up top and this one on the bottom. Okay? It resembled them both. Because if I covered up the n, that looks like a geometric series. If I cover up that looks like the harmonic series. Okay? So we compared it to the geometric series. What if we compared it to the harmonic series? What if we compared it to the harmonic series? So if we call this AN, and we let this be BN, let's go over and do the same thing we did before. Same thing we did before. Note. AN is how does our series compare to the harmonic series? Greater than or less than inside? Greater than or less than. It's got a bigger denominator. All right. So what does the direct comparison test say about our series, comparing this? Okay. The answer is absolutely nothing. Okay. DCT, all right, let me just put this way. Using or comparing right, is useless since brackets DCT does not apply. Why is it useless? Because you're comparing, if you're going to compare it to a bigger series, the bigger series has to converge. I'm going to back up one slide. I'll come back to this. Using the direct comparison test, if you're going to compare it to a bigger series, the bigger series has to converge. See, if the bigger series converges, then the smaller series does. Right? But if the bigger series diverges, what do you know about the smaller series? Nothing. Notice the conditions here. There's two ifs. If the bigger series converges or the smaller series diverges. If the bigger series diverges, this theorem doesn't say anything. You've just shown a bigger series diverges, the smaller series could still converge. Right? Right? Does not apply. Right? Because you compared it to a bigger series, which this one diverged. So if that one diverges, it's bigger than this one. You don't know what this one does. It could diverge. It could converge. You don't know. Turns out it converges. Why does it converge? Because of this. Right? Because of this. Now look down here what I have written at the bottom. Number one, there is no point in showing a larger series diverges. Two, there is no point in showing a smaller series converges. Because if a smaller series converges, that sigma an converges, that isn't the condition for either one of these scenarios. So there's no point in comparing to a smaller series that converges or a larger series that diverges. This is the main point of confusion in the direct comparison test. I'm even going to write. These are the main points of confusion in using CT. So what I try to do this in all my teaching. You can tell me how I can do it better, because I know I can do it better. I know I can do it better. I try to probably overemphasize, in most cases, the points that people stumble. Right? The points that people stumble. And I know, I'm so like your mom, right? Right? You watch it when you cross the freeway, right? Why? That's where people get killed. They don't kill going, they don't get killed going down the driveway usually, right? They get killed on their way to school with, crossing a big road or something, right? And so I'm trying to tell you where people trip up, and the reason why is I've tripped up all the time. Oh dear.
Can you go back real quick? 1 second.
Yeah, this is kind of cold season. It's kind of a bummer, man. I told you I had a cold over Easter break. Went down to see my daughter and granddaughter, Edmund. The granddaughter had caught a cold from somewhere in the, I don't know, probably the church nursery, we think. She's at home daycare, right? So she doesn't hang out with a lot of other kids, a lot. She has a couple of girlfriends she hangs out with. But anyway, went down there. We all caught her granddaughter's nasty cold because we were all mauling her to death. She's so adorably cute. Oh yes, right here. Let me see here. Brand new picture right there. Anyway, so it wasn't a really bad cold as colds go. Little fever, runny nose, eyes, sniffles, and we didn't worry about it. But the good news is we got over it real quick. The Friday before of spring break, I was a sniffly, fevery mess on Friday, and we had to drive back all day on Saturday. And Monday, I had to be back in the classroom. I mean, I couldn't cancel a class. You wouldn't know what to do if we canceled a class. So I know. But Saturday, it just started clearing up. And what happened here? Oh, by Sunday morning, I was all better. I even went to church on Sunday. I could have taught on Sunday if I had to. So, anyway, I think if yours is anything like mine was, which I hope it is, it won't last very long. All right, it won't last very long. All right, moving on. This guy. Yeah. Question. Now you remember I said back here, I think you had stepped out of the room, Cassie. When you're looking at whether a series converges or diverges, you have to, and you can only do this by experience, you have to be able to develop a suspicion. Do you suspect that it's going to converge, or do you suspect it's going to diverge? How do you do that? Well, one way is this. Look at this. You have n in the top, cosine n squared minus cosine n. Okay. Now, do you suspect that converges or diverges? I suspect it diverges. I'll tell you why. Because cosine, for one thing, don't do this. Cancel. Every time you do that, somewhere a kitten dies. It's sad. It's very, very sad. Right. Right. If you were in intermediate algebra, you know, this happens all the time. Don't do this in calculus. No, please don't do it in calculus. Right. You could cancel if there was an in outside there, outside the cosine, you could cancel the ins. But not from inside the cosine. Number one. Why do I suspect that diverge? Why did you suspect it diverges? Just a hunch, or you have a reason, or?
Because there's gonna be a zero on top.
Okay. All right. It will be a zero. It'll start with a zero on top. Zero on top is okay. That means you have a zero first term, right? I'll tell you why I suspect it diverged. Is these, that is a little bit like 1 over n. Right? Because that n would cancel out of those. So that behaves like 1 over n, which diverges. Okay? This is between zero and 1. This cosine only goes between minus 1 and 1, right? Cosine goes between minus 1 and 1, but if I square it, it's between 0 and 1. So something that blows up to infinity, and if you do a plus or minus 0 or 1 in the bottom, that's not going to make a lot of difference. So I suspect it diverges. And I really can't overestimate the value of developing these suspicions, like being able to, you know. Now, the thing is, sometimes you're wrong. And if you're wrong, the process will bear that out. But why is it valuable to come up with a suspicion? Okay. Because if I suspect it diverges, look at the direct comparison test. Look at the slide of the direct comparison test. If I suspect it diverges, what kind of series am I looking for to use the direct comparison test? If I suspect this series diverges, what kind of series am I looking for? What kind am I looking for? A smaller series that diverges, a smaller series that converges, a bigger series that, what am I looking for? The direct comparison test only gives you one way of showing something diverges. The DCT offers only one way of showing a series diverges. By the way, it only offers one way of showing a series converges too. To show a series diverges, you need to get a larger or smaller series. larger series, and show that that larger series does what? If I had a larger series, how would I use a larger series to show this diverged? What do you think? It would say in Italian, "Che ne dice?" Che ne dice? Che ne dice Jesus? What do you say? What do you say about ne is the way you say about it. Che ne, che is what? Ne is about it. Dici is say. And so it's a way of saying, what say you? You need a smaller series, a larger series that diverges or converges. Here's your choices. Smaller, larger, that diverges or converges. I'll give you a hint. There's 4 boxes. The direct comparison test only applies to 2 of them. 2 of those boxes don't do you any good at all.
I'll say diverges larger.
So diverges larger. So Jesus is down here. What say ye? What say thee? What say thee? Ye is plural. The Elizabethan English had a different word for second person singular and second person plural, like you and y'all. So what kind of series are we looking for? Smaller or larger series that converges or diverges? So we have Cassidy here. Okay,
JC.
is that it? You willing to bet your double wide on that? The direct comparison test applies in which 2 boxes? This box. And applies to this box. Showing a larger series blows up doesn't say anything about the smaller one. Okay. It's okay, guys. Okay. What we're doing is you take your strikes in batting practice. Take your strikes in batting practice. You know, I don't know. You guys probably don't pay attention. But the other day I was walking back from a meeting. I stopped and watched the practice the other day for a few minutes outside the fences. I didn't go in the stadium.
When?
It was last week sometime. I can't remember which day, but it was fun. It was fun watching. There was some guy was taking a batting practice up there, and they were behind, what do you call that screen, the pitching screen?
Oh, the L screen.
Yeah, L screen, right? He's behind the L screen, and we're taking. He was taking batting practice and obviously fielding, right? And then there's some guys in the outfield, you know, practicing, I guess, throwing or something. When I was little, we'd say they were playing catch, but I know that's doing something else. You're practicing probably harder throws and good fielding throws. Look like they were practicing. I don't know. What do I know about baseball? Yeah, these 2 here are the only boxes that apply. Okay, so this box showing a larger series diverges doesn't say anything about the smaller one. Okay, so now you can retake for half credit, right? You can make corrections for half credit. Which of these 2 boxes should we go for if we suspect this diverges? A smaller series that diverges, he said. What about you? Smaller series that diverges. Exactly. Because this shows that something converges. Right? That's how to show, I'm sorry, diverges. Sorry. Listen to me. That shows the series diverges. This would show the series converges. If you show a larger series converges, your smaller series converges. Okay. So let's back up. What we need to find a smaller series that diverges. Okay. All right. Question. What sign goes in there? What sign goes in between there? Greater than or less than? Jesus says less than. You say? It's actually, it's a Monday, guys. Because this one has a smaller denominator. It's got the n on top. This is going to have a smaller denominator. It's going to be bigger. So this is going to be smaller than that. Okay? For n being positive. Right? N being positive. So this is an, right? This is bn. Here we have a smaller series. This is a smaller series, right? We add them up. Does sigma 1 over n diverge or converge?
The what?
Does sigma 1 over n diverge or converge?
Converge.
What do you say?
No, diverge.
Diverge. Okay. All right. He was going to throw him out at third. A third decided to do the cutoff at home. All right. How about you? Does sigma 1 over n diverge or converge? Diverges. Why? P series, P equal 1. Right? It's a P series, P equal 1. Ninja. Right. Quick. You don't want to be stuck on that. Right? And that's why this stuff is so unforgiving. The stuff we did even last time makes this stuff either live or die. So, time to write our conclusion. This one diverges. We have a smaller series than this, the one we're interested in. A smaller series diverges means our series diverges by the direct comparison test. Okay? So let's write our solution. Sigma. Uh-oh. I don't like what I saw there. Sorry, did you see that? You should have seen it. You should have seen it. I wrote on the board and it was delayed. So that means we're about to have a crash or Rooney. Crash or Rooney. We actually got through quite a bit today without having a crash. Right? So sigma n equals 0 to infinity n squared minus cosine squared n diverges by the dct since what? N over n squared minus cosine squared n is greater than 1 over n, and sigma 1 over n diverges. It's a smaller series that diverges as a p series with p equal 1. That's our answer. That's our answer. And the key to the whole shebang is understanding this box over here, this little grid over here. Right. That's the key to the whole shebang. So we started up here by developing a suspicion. Now, had we suspected at the beginning that it converged, we would never have been able to make any of this work down here. It never would have worked. Because if we think it converges, we would be in this box over here, right? If we thought that converged, we'd be trying to find a larger series that converges. And we wouldn't be able to find one. Now, we're dealing with all positive terms here, right? All positive terms. Remember, the direct comparison test has both series with all positive terms. Right? Yeah. So that's a good one. Now, ooh, look what we got here.
You go back.
Okay. We have a homework problem. Do next time. Converge or diverge. What do you do if you have a plus sign right here? What do you do if you have a plus sign and I give you a hint?
You gotta be less than. You gotta be bigger.
Does that converge or doesn't? That's interesting. That's very interesting. I give you a hint. Compare it to this guy. Compare it to that one. Compare that to that. And then you have to decide what this one does. Okay. All right. And then we have a retro problem. Yes, ladies and gentlemen.
Can you go in the last one?
Okay, I will. The retro problem goes back to chapter 6, the final. This is a differential equation. You have to decide what kind of differential equation it is, apply the appropriate method, right? And that's the solution.
So why didn't we say that it converges again? Like, what do we have to do?
Well, why do I say this converges?
No, the one that we just did.
This one?
Yeah.
This one doesn't converge.
I know, but what if we suspect?
Oh, if you did say it converges, you wouldn't be. If it did say it converges, what do you have to do? You have to find a larger series that converges. If you think this converges, to use the direct comparison test, you have to find a slightly larger series that converges. Okay? All right. Now, we have a couple of other tests available to us here. So, for example, I use the p-series test here to show that that diverged. I could also do the integral test, right? That, and this integral those both converge or diverge, remember, by the integral test? So you could equally well have said this diverges since this integral does. But you'd have to show that integral does. Here you're using a theorem. You're using our p-series theorem. But if you would have said converges here, you would not have been able to find a larger series that converges. Because there won't be. Yeah. So this guy, how would you show this guy converged or diverged? And is this guy bigger or smaller than that one? If it didn't help you, why would I give it to you as a hint? Just to watch you suffer. No. Okay. So you have to decide, does this converge or diverge? Which one do you suspect? It's very similar to the last one, except we've got a plus sign there. And how does it compare to this one? How does that compare to this? And what does this one do? You see all the questions to answer? So we've spent a long time today talking about just a few slides, but they are very, very, very important. And if you wait 3 or 4 days to look at this, there's going to be weeping and gnashing of teeth. You won't remember any of it. All right, so don't do that. I think we're out of time. We'll leave it there. Tonight, I'll be at Spark, 8 to 9. All right. I got 2 classes that test this week. Definitely count on a Chapter 9 test next week. Absolutely, positively. This week and next week are going to be fairly intense in terms of the number, the amount of material we have to cover.